Alright, welcome to 4.18. We're going to prove the Pythagorean identity and use it to prove other identities. And this is one of the more important things that we're learning in this unit, and it actually kind of carries over into a lot of different areas of math. It's where the equation for a circle comes from, and it's overall just very, very useful. So we're almost at the end, but that doesn't mean what we're learning isn't incredibly important. In fact, I might say that this is the most important thing that we're learning in this unit. To start off, let's go ahead and just remind ourselves of the Pythagorean theorem. So go ahead and just write out the Pythagorean theorem. You can assume that we have a right triangle with side A, side B, and side C. Alright, so you'll remember, of course, that the Pythagorean theorem says that if you have a right triangle, then the sum of the squares of the smaller sides, a squared plus b squared, that's got to equal the square of the hypotenuse. Okay? Nothing too crazy, and of course, if you have a triangle where this is the case, the reverse is true. So if you find that a squared plus b squared equals c squared, then you know you're dealing with a right triangle. Okay? Alright, so let's come over to our unit circle here. And let's just consider any point on the unit circle. So let's consider this point here. Okay? So this is a unit circle of radius 1. So that is the distance 1. And then this point, of course, let's just label this point. So this point here has an x coordinate, and it also has a y coordinate, right? And what is the value of the x coordinate? Well, the value of the x coordinate is the distance traveled in the x direction of that point. So the length x is this length right here. Okay. And the y coordinate, of course, is the distance in the y direction. So it's that distance there. Now what I want you to do is I want you to pause the video, and I want you to, and of course, hold on, let's just remind ourselves this is a right triangle. And I want you to use the Pythagorean theorem to apply it to this triangle here. So if this triangle is a right triangle, which we set it up to be, what does the Pythagorean theorem tell us? So hopefully you remembered, well, the Pythagorean theorem tells you that the sum of the squares of the smaller sides will equal the square of the hypotenuse. So for this right triangle, we have x squared plus y squared is going to be equal to 1 squared. And I would put the square there, but 1 squared is 1, right? Well, now let's remind ourselves, what is the x-coordinate of this point here once we've rotated this many radians? Well, this x-coordinate is cosine of the angle that we've rotated. And the y-coordinate is the sine of the angle that we've rotated. So this x distance is no more than, it's simply the cosine of theta. And the y distance is the sine of theta. So I want you to pause the video again, and now I want you to rewrite this expression and use cosine and sine of theta. So the x distance is the cosine of the angle that we've rotated. And we know that the x distance squared plus the y distance squared is equal to 1. So we can rewrite this identity here. We have that the cosine of theta squared plus the sine of theta squared is going to be equal to 1. Okay? And I'll just stop and think about what this is saying. So any point that I am on my unit circle, no matter where it is, the x distance is the cosine of theta. And the y distance to that point is the sine of theta. So even if I were considering this point over here or this point over here, that's still the case. And we can construct a right triangle using the x distance as the horizontal side and the y distance as the vertical side. And that will construct a right triangle with the hypotenuse, which will always be 1, because my radius is always 1. So it's always going to be a case that the x coordinate squared plus the y coordinate squared will equal 1 squared, or 1. And the x coordinate is always, it's defined as the cosine of theta, depending on how far I've rotated. And the y distance is defined as the sine of theta for the angle that I've rotated, the number of radians that I've rotated around my unit circle. And so this is always the case. No matter what your value of theta is, no matter how many radians you've rotated, maybe it's 5 radians, maybe it's 10 radians, maybe it's 7 pi radians, this will always be the case, because no matter what your angle that you're turning, you're still on the unit circle. You're just rotating around it, and no matter what point you end up on, it's always going to be the case that the cosine of theta squared plus the sine of theta squared must equal 1. And we actually can rewrite this. The way that we write cosine of theta squared is we actually put the squared right after the cosine. So this is just how it is written. It's written as cosine theta squared, that's how it's written, plus sine squared theta is equal to 1. And this is the Pythagorean identity. In fact, this is where the formula for a circle comes from. If you were to graph x squared plus y squared equals 1 on your coordinate system, you would get a circle of radius 1. In fact, I encourage you to go to Wolfram Alpha right now, type this in, say plot x squared plus y squared equals 1, see what you get. Then go and plug in cosine squared plus sine squared equals 1 and see what you get. And what you will end up with is a unit circle. Okay? And you might try this out. Try changing the 1 here. So you'll notice if you were to change this to a circle of radius 2, well, if you plugged in 2, then you're beating all the points that are on a circle of radius 2. Okay? So very powerful, very interesting, and also very simple, very elegant. So what I want you to do now is you're going to pause the video in a second. What I want you to do is I want you to rewrite this. So I want you to rewrite this first in terms of, so I want you to rewrite this formula for cosine squared of theta. And then also want you to rewrite it for sine squared of theta. Okay, so pause the video and do that now. Alright, so hopefully you can see here that if I want to isolate the cosine, I just need to subtract sine from both sides. So the cosine of theta squared is going to be, or cosine squared theta, either way, is 1 minus the sine squared. And similarly, the sine squared is just going to be 1 minus the cosine squared. Okay? So this actually makes it very easy to solve for the cosine if you know the sine, because you plug in the square of the sine, and 1 minus the square of the sine is equal to the square of the cosine. So if you were to square root both sides, you'd see that you'd be able to solve for cosine. Same here, if you square root both sides, the sine squared, square rooted, is going to be just the sine, and so you'll be left with the square root of 1 minus cosine squared. Okay? So this is the kind of the preliminary effect of the Pythagorean theorem, and it'll allow us to solve some situations where we either don't know the cosine or the sine or even the tangent very quickly without looking at our unit circle. Of course, it's always good to have the unit circle in mind, and hopefully we've almost sort of memorized it to the point where we don't need to draw it out, or if we do, it's very quick and painless. Let's see how we can use this. And this is a sort of simple problem. You might, it's maybe so simple that you can just imagine it in your mind, but the idea is that we want to see how this is useful so that when we can't actually picture this situation in our mind, we can use the Pythagorean identity. Okay, so here's the situation. You know the angle theta that you've rotated is between pi over 2 and pi radians, and you're told that the sine of theta is 1/2. And we want to figure out what's the cosine of theta and then what's the tangent of theta. So pause the video now and try and find the cosine of theta and utilize the Pythagorean identity. Don't just use your unit circle. Alright, hopefully that went well. What I want you to think about is, okay, well, we know the sine of theta, right? You know it's 1/2, so this sine squared is going to be 1/2 squared. So if I utilize this Pythagorean identity, I'm going to be able to solve for this pretty quickly. So remember, we're looking for the cosine of theta, so let's actually just start with what we know. We know that the cosine squared of theta is equal to 1 minus the sine squared of theta, right? That was what we just solved for on the last page, right? Just by subtracting sine squared from both sides. And we know that the sine of theta is 1/2. So this is where there might be a little confusion here. How do I deal with this square? Well, remember that sine squared, this means that I'm taking the sine of theta and squaring the whole thing. So this is going to be equivalent to 1 minus, and the sine is 1/2, and I'm squaring it. Not too bad. So the cosine squared of theta is equivalent to 1 minus, and 1/2 squared, you could think about, that's 1/2 times 1/2. Another way of thinking of this is 1 squared over 2 squared. Right, so it's going to be 1/4. And so we now know that the cosine squared of theta is equal to 3/4. Well, let's keep going because we want the cosine, not cosine squared. So just like with any number, we can use the inverse operation of squaring. We can square root both sides. And remember that we have to, when we square root, set over here, we have to include that it could be plus or minus. And I want to talk about why that is very quickly. So when you square something, it doesn't matter whether you're squaring a negative number or a positive number. You're always going to end up with the positive version, right? So what could cosine squared be? Well, it could be either a positive number or a negative number squared, right? So the cosine, right, what we're looking for, the thing that we're squaring, it could be either positive or negative, because when we square it, it'll end up turning positive. So when we square root both sides, now on the left side, where we've got the cosine of theta, and that is equivalent to plus or minus the square root of 3/4. And this will help us see why we have that positive or minus right here, because cosine, remember I'm squaring it, right? I know cosine squared is equal to 3/4, right? And, well, cosine could be either positive or negative. When I square it, it's going to equal 3/4, whether it was the positive or negative version. So what it could be equal to is either a positive or negative version, and we'll find out which one that has to be based on theta in a second. So on the right side here, well, what's the square root of 3/4? That is the square root of 3 over the square root of 4, which is the square root of 3 over the square root of 4, which is 2. And it could be either positive or negative. Positive or negative. square root of 3 over 2. Well, which one could it be? So think about our unit circle here, and you just want to briefly imagine a unit circle. So I will draw it right over here, right? And think about cosine, right? So cosine is positive, right? It's positive over here, right? And then over here it's negative. Okay, so think about sine. The situation we know is we know sine is 1/2, okay? And we know that the angle theta that it's rotated is between pi over 2. It's greater than pi over 2 and less than pi. Well, pi over 2 is here, and pi radians is right there. So it's somewhere in between here, somewhere in this coordinate here. And so what is cosine over here? Well, the cosine is negative. So the cosine that we're looking for is going to be negative root 3 over 2. Negative root 3 over 2. Alright, so now I want you to pause the video. I want you to find on your own the tangent of theta. I want you to post in your comment the value you found for the tangent of theta and how you found it. Be very careful that you don't just want to post what the tangent of theta is. You want to post how you found it. So might want to go back into your notes and remind yourself how to compute tangent. And we're going to move on, and I'll introduce you to one more question, and then that'll be it. So using the Pythagorean identity, and you'll probably just want to write that out again to remind yourself what it is, show that this following equation is true. So I'm going to let you go at this on your own. And I want to remind you, I want you to just think, what does it mean to show that an equation is true? Well, to show that the left side is equal to the right side, you need to show that the left side is the same as the right side, right? So if we can manipulate either the left side or the right side to look like the other one, and we show that the left side is equivalent, it's the same thing as the other side, then we've shown it to be true. So that is our goal here, just a reminder. I just want you to go through, and I want you to try this on your own. I need to be able to see that you've given it some attempts, and obviously there's some steps that you can make. You know what cosine squared is, you know what sine squared is. There's a lot of different steps you can take to start off. So give this a try. Make sure to post a comment, not only with the tangent of theta that you found in the last problem, but also with a question or an answer. See you guys on Monday.